Hello, Rebecca. Today we are getting to move on to the next part of our curriculum, which is Structure 1.2, and we're going to be talking about the nuclear atom. So we'll talk about the nucleus, what's in atoms, the subatomic particles, what it means when we have different ratios of different things. Lots of different stuff. You probably know some or a lot of this stuff, but we're gonna try and dig a little deeper as we look through all this stuff, and we'll look at some kind of advanced techniques that chemists use as well to help us decipher what types of nuclei or atoms we have, because chemists build really complicated and interesting machines to try and figure out exactly what we have in a sample. So that's kind of the end of this 1.2. Before that, we'll talk about the basics. So today, I would like to start by having you draw as many representations of a hydrogen atom as you can. So feel free to look at the periodic table if you want. There's really not wrong answers here. I just want you to try and come up with as many representations of hydrogen as you can. So take a second, pause the video, in your notebook, write down as many as you can think of. Okay, so there are lots and lots of different options and answers here. Here are two you could have drawn or written right on the periodic table. We have a little box for hydrogen, right? It has a symbol. That's a great way to represent hydrogen. You could have written the word. That is a representation of it, right? You could have given its atomic number. Maybe you drew a model of it, like this is a Bohr model that shows its nucleus and its electrons. There are lots of different ways to do this, more than I have mentioned. But that's just to get you thinking. There are lots of ways to represent these atoms. But we want to know what the representations mean as well. So yeah, this is part A of 1.2. The nucleus is what we're going to talk about today. We'll talk about electrons in part B, I believe, or maybe that's 1.3, I can't remember. But we'll get to electrons eventually. We'll cover them briefly here though. So I'm going to play this video for you. Hopefully it works. If not, I'm also going to post it in ManageBack so you can watch it there. But it is just kind of a silly little video that is showing you size comparisons on just how small an atom really is. So here we go.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? Well, it's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. Now let's go and grab all of the nuclei from a typical car. Now cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of a nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired.
All right, hopefully that worked. So, now I'm going to have you look in the data booklet. And I think I mentioned this briefly in our last lesson, but the data booklet is something that you get for the IB exam, and you'll also get for all the exams that I give you. And it has a bunch of different things in it that will be helpful to you, including periodic tables and all of this information here. So the mass, relative mass, charge, and relative charge of the 3 subatomic particles, right? Proton, neutron, and electron. These are the parts of the atom. So hopefully that has been printed off for you. If not, it will also be posted on ManageBack, so you could look at it there if you need to. But I want you to take a couple minutes, see if you can find this information, and then write it down in your notebook. And then, so yeah, pause the video, and then after you get a chance to do that, I will talk about it. So, hopefully you're able to find all of that information. It is important to be able to use the data booklet quickly because it will help you on the test, but you don't have time to not know where things are in it. So we're going to practice looking for things in that book throughout the year, and you'll get to know it really well. But here are the answers. The proton, its mass in kilograms is 1.67 times 10 to the negative 27. That is absurdly tiny, right? It's kind of unimaginably tiny amount of mass. But it does have mass. And the neutron is very close, right? 1.675 times 10 to the negative 27. These are both have very little mass compared to things we're used to, but on the subatomic level, they are actually much, much bigger than the electron, right? Because this exponent is a larger negative exponent, so that means it's smaller, right? The electron is 9.109 times 10 to the negative 31st. And this type of writing numbers is called standard notation, or sometimes it gets called scientific notation. And it's useful because we don't have to write out all those zero places. But when you see the negative exponents, just remember that that means it is a very tiny number, right? And the bigger the negative, the smaller the number is. So protons have and neutrons have just a tiny bit of mass. Electrons have even less. So when we start talking about them, we're not going to use the kilogram numbers. We're going to use something called relative mass, or sometimes it gets called atomic mass. And so for that, we consider that the proton and the neutron have about the same mass, and we're going to call them 1. So one proton has a relative mass of 1, one neutron has a relative mass of 1. And the electron has so little mass, we're going to call it negligible. Or for the cases of calculations, we're just going to say it's 0. When we think about the charge of each of these subatomic particles, protons have a charge of 1.602 times 10 to the 19. This is coulombs, which is an electrical unit. Electrons have the same exact charge, right? 1.602 times 10 to the 19. Protons are positively charged, electrons are negatively charged, right? But they have the same value, the same strength of charge. And neutrons are not charged, so they are 0, right? Again, we're not going to use this Coulomb value because it's kind of hard to calculate with. So when we're calculating charge and we're thinking about atoms, we will use the relative charge. So a proton is plus 1, it's positive, and an electron is minus 1, it is negative, and neutron is 0. So hopefully you're able to find that stuff in there.